Good afternoon, I'm Luca Modenese from Imperial College London, and it's a great honor for me to present this work that was selected for the Athanasiou Postdoctoral Award in 2021. This work was done in collaboration with Josef Kout from the University of West Bohemia in Czech Republic. The topic of this presentation is the anatomical representation of skeletal muscles in personalized musculoskeletal models. A musculoskeletal model is a computational representation of the musculoskeletal system used to perform biomechanical analysis, for example, investigating the function of a muscle. These models are called personalized when they are created using information that are specific to a certain individual. In this presentation, we call personalized models created from three-dimensional surfaces of bones and muscles obtained from segmentation of medical images. If we consider a gluteus medius surface model, as in this slide, and want to create a biomechanical model to investigate its function, we have two main options. We can create a finite element model, which capitalizes on the 3D muscle shape, can include fiber arrangements mapped from predefined templates, but it's overall complex and computationally expensive approach to simulate quasi-static scenarios. The other option is to create a musculoskeletal model, a multi-body system which is much simpler and faster to execute, that can be used to simulate dynamic tasks, but in which the muscle is represented as one or more straight lines of action acting like contractile ropes. In other terms, the subject-specific volumetric information is lost. Before introducing our new approach, I would like to explain how skeletal muscle anatomy is represented in standard musculoskeletal models. The two main aspects influencing the anatomical model are the muscle discretization and the fiber resolution. The muscle discretization indicates how many fibers or lines of action are used to represent each muscle. And here you can see two examples of lower limb models with very different discretization level. The fiber resolution, instead, indicates the number of straight line segments used to represent each line of action. And here you can see the difference in smoothness, but also total length, between a representation of the quadriceps that uses a large number of straight segments and one that uses very few. Both these aspects of the musculature models usually depend on dissection data and are not under the control of the model. After introducing these concepts, the aims of our work become straightforward to understand. We wanted to implement an automated procedure to generate anatomical muscle models with customizable discretization and fiber resolution levels. We also wanted this method to be computationally fast with respect to finite element models, in the order of magnitude of seconds, both in generating the geometries and computing muscle kinematics. For this investigation, we will use the LHDL anatomical dataset, a cadaveric dataset in which bone and muscle geometries have already been segmented by the original authors. We will focus on the iliacus, psoas, gluteus maximus, and gluteus medius muscles, for which the muscle attachments have been directly measured during the dissection process. The method we developed consists of two steps. The first one is a fiber decomposition step, where starting from a muscle triangulated surface model and from its muscle attachments on the origin and insertion bones, we obtained a desired number of muscle fibers. This step starts by defining a scalar field on the muscle surface, from which the attachment sites have been removed, and then in using it to define as many isolines as the desired straight line segments on the muscle fibers plus one. A cubic template defining the fiber arrangement and including as many fibers as desired by the user is then considered and sliced, and the fibers are mapped to the corresponding muscle sections. In this way, a final muscle representation is obtained in the reference pose defined by the surface models. This approach allows the user to vary the number of fibers and straight line segments as desired. And here you can see the results of varying these two parameters for the gluteus maximus. On the y-axis, the number of fibers is increased, So you can see the muscle volume being better filled, while on the x-axis is the volume of straight segments to be increased, leading to smoother lines of action. In the diagonal, you can see the combined effect on the muscle representation. And on the upright position, the model obtained with 144 lines of action and 20 straight line segments each is represented. These muscle fiber decompositions are fast. They take milliseconds to be executed, but they generate just a static model, while we are interested in simulating joint and muscle kinematics as well. The second step of our proposed method implements the fiber kinematics, meaning how these highly discretized muscle representations move in space when their attachment bones are changing their position and orientation. The muscle kinematics was implemented without connecting the fiber points to their closest bone, as this could have led to some incorrect representation. We opted instead for a solution in which points are moved in space using a blending weight approach that takes into account the position of each point within the fiber length, so that points closer to a bone are influenced more by its movement, and points that are midway are under the influence of both attachment bones. The algorithm is currently implemented as an OpenSim plugin, and we are planning to release it in the near future. OpenSim is a popular software for biomechanical modeling and simulation that we used for our analysis. Here, you can preview the easy setup of the analysis and the realistic visualization results when the gluteus maximus model is visualized and the hip flexion angle modified. Of course, we also wanted to know if our muscle model were credible biomechanically, so we made an effort to validate our approach. We created a model with highly discretized muscles using the LHDL dataset, decomposing each muscle in 100 fibers of 15 straight line segments. Then, using exactly the same anatomical data, we also generated a standard straight line musculoskeletal model, where we ensure the highest anatomical fidelity by defining the lines of action with the help of the same muscle surfaces used to generate the first model. For both models, we then calculated the moment arms for all the available muscle fibers, simulating 3 functional hip joint movement, a flexion extension, an abduction abduction, and an internal external rotation. For these same movements, we also obtained values of moment arms from a validated finite element model, cadaveric specimens, medical images, and a physical model. These datasets were available from the previous literature. The moment arm indicates the mechanical advantage of a muscle line of action in generating joint moment, and we consider it a key quantity to assess the quality of our biomechanical models. These are the results we obtained for the hip flexors, the iliacus and the psoas. In this slide, each row represents a hip joint movement, and on the left side you can see the fiber kinematics of the highly discretized models, while on the right side the muscle fibers moment arms are compared. The moment arms estimated from the highly discretized muscles are generally in good agreement both with the straight line model created from the same anatomical dataset and with the previous studies considered for validation. There is a disagreement only for high hip flexion angles, over 40 degrees, where the moment arms of our model decreased, while those in the musculoskeletal model and the validated finite element model increased. This is because our muscle fibers kept moving with the femur and stuck to that bone, rather than detaching and providing a larger hip flexion moment arm. It is worth mentioning that all simulations were performed in seconds, which for us was a satisfactory performance. When we looked at the results for the hip extensor muscles, the gluteus medius and the gluteus maximus, we observed agreement among all the models and the data considered for validation. Here, the only issue we noticed is that few muscle fibers penetrate the bone geometries at the extremes of the ranges of motion for the hip abduction and hip external rotation movement. In summary, In this work, we have presented a fully automatic method for creating muscle models from segmented surfaces. These models can be fully customized in terms of number of fibers and their number of straight line segments. The moment arms of the hip muscles generated with this technique compared well with those reported in the literature, especially in the joint range of motion typical for walking. The proposed method presents some limitations. The main one is the need for the muscle attachment areas on the origin and insertion bones, required to generate the initial fiber decomposition. We are currently working on a non-rigid registration technique to mapping existing cadaveric dataset on new geometries and solve this issue. We have also started applying our approach to in vivo datasets, and we will soon be able to determine if the anatomical model influences the muscle force estimation in optimization-based musculoskeletal models. We strongly support open science, so all the models and code required to generate the results and plots that you've seen in this presentation are available from my GitHub account. All the relevant links and further details and analysis can be found in the open access publication connected with this presentation. I want to conclude by acknowledging my colleagues and co-workers and, of course, my source of funding. Thank you for your attention.